Welcome to all of you around the world joining us on this edition of the MIT Firehose Chats. I am Carol Urbano from the MIT Museum, and I am your host today. Jerome Wiesner, former MIT president, once said, "Getting an education from MIT is very much like drinking from a fire hose." That certainly would be a lot to take in. Fortunately, today we're just going to take a sip from that fire hose and we're going to talk about autonomous science. And we'll be working with our featured guest, Marlyse Reeves. Marlyse is a third-year PhD student in the MERS group at MIT, studying under Professor Brian Williams. Her current research interests include robust execution, active learning, and active sensing in multi-agent autonomous observing systems. And I think I'm going to bring Marlyse on to tell us a little bit more about what that means. Welcome, Marlyse.
Hi, Carol. It's exciting to be here. Let me just share my screen. Are you seeing my presentation?
Yes, I am.
Great. Okay, so I'll get started. Yes, I'm Marlyse. I am a PhD student studying computer science, specifically with a focus on robotics and autonomous systems. Today I'm going to be talking about some research that my lab is heavily involved in. And so the title of my talk today is Autonomous Science, Programming Robotic Explorers. So let's just jump right in. So first, a little bit about me. I grew up in Southern California. I lived super close to JPL, the Jet Propulsion Laboratory. For those of you who don't know, JPL is kind of the organization, a branch of NASA responsible for putting rovers on Mars, amongst a lot of other really cool things. So in addition to that, I am and was a huge science fiction buff. Pictured here is my favorite sci-fi TV show, Firefly. So couple the fact that I live close to JPL, I love sci-fi, and my dad had a telescope when I was growing up, and I was pretty much a space nerd from the start. Then when I was in high school, I joined a robotics team, a first robotics team. I helped start it at my school. I'd never had coding experience before, but I kind of found myself really enjoying it. So that kind of turned me on to robotics. And then I was fortunate enough to get to go to MIT to be in the aerospace engineering department. So I kind of went back to my aerospace space side at MIT. And I loved the aerospace department. I really wanted to learn how to be an engineer, how to learn how to solve problems, how to create things. But all the while, I was still kind of getting called back to AI and robotics. So after I graduated MIT undergrad, I decided to go back to MIT in the computer science department and learn some more about programming, algorithms, and AI. So now I'm currently in the Model-Based Embedded and Robotic Systems Group, or MERS as we like to call it, at MIT. And as you can kind of see, I have two major trends in my life. I love space and I love robots. So let's talk about that. Let's talk about autonomy in space. So as many of you probably know, this is Mars Curiosity, or more specifically a selfie of Mars Curiosity, which has been exploring the surface of Mars for almost 7 years. So how smart is Mars Curiosity? It has a lot of sensing capabilities, cameras, atmospheric measurements, environmental measurements. It can keep itself alive. It regulates its own temperature, power, data. But since 2012, it's only actually covered about 13 miles in 7 years on the surface of Mars, which to me is always a crazy fact. 13 miles, 21 kilometers. So if we think about how the rover is controlled, it's by these people sitting in this room on Earth, sending commands up to the rover on Mars with about a 7-minute delay in communication. So you can imagine how operations go. The people in this room send a command. They have to wait 7 minutes to see a result for that command to reach Mars. Then Curiosity executes that command. Then they have to wait 7 minutes to get data back, etc. So that's kind of a slow process, which is one of the reasons why Curiosity hasn't driven very far, because they have to be very careful. And this is kind of how most spacecrafts and planetary operations have been so far. Autonomy is often perceived to be very risky when there's no kind of person in the loop. So, and it's very expensive to send things into space. So this kind of has worked fine, but if we want to start exploring deeper in our solar system, like to places like this, like Europa, which is a moon of Jupiter that we think might have life in our solar system, if we're going to start to explore there, we need more autonomy. This is an hour time delay, and we know very little about this place. So whatever we send there has to be smarter. So this is kind of like the big question that my lab is trying to answer. How can we do untended, unsupervised exploration in an unknown environment? And of course, how do we even test that since we're sitting here on Earth? And we can't readily send stuff up to space all the time. Well, one thing we do is we use the oceans. So the oceans are actually a really, really great analog for space exploration for a lot of reasons. The oceans are hands down one of the most unexplored places on Earth. We can really simulate what it's like to be in a new environment that we haven't seen before. Additionally, communication underwater is really challenging. While there might not be as much distance as if we were communicating from something way up in space, there are a lot of challenges. Acoustics is kind of the best way to do it, but the range is really short. You have to be really close to the vehicle that you're communicating with. Another thing we can do is communicate via satellite, but the vehicles have to be on the surface to do that. That's another challenge, but it's a good simulation for what it's like to communicate infrequently with something. Additionally, oceans are pretty hazardous and dangerous places. There's currents, there's sea life, there's other people boating and shipping things across the water. There's underwater chemical vents. The list goes on and on for all of these things that if we are trying to control an autonomous system, that we have to be able to control it safely. And above all else, there is really interesting science to be done in the oceans. There's so much we don't know. And so this is kind of the domain that we have chosen to kind of do our research. And also there's just a lot of really cool vehicles and robots that people have developed for exploring our oceans. So what does robotic ocean exploration kind of look like? So typically we start with some engineers and scientists. They kind of have an idea of what sorts of phenomenon they're interested in looking at. And then the engineers kind of program in step by step what each vehicle can do. The engineers are handwriting these scripts. So basically, I need to go to this latitude and longitude, and then to this latitude and longitude, and then I need to surface. And the engineers are all doing that by hand. Then the vehicle is deployed. It just kind of executes that script step by step. And then the scientists come back, they take a look at the data, they process the data, decide what to do. The engineers kind of take a look at the vehicle, see if anything happened to it while it was underwater, and then they figure out what to do next, and the whole process kind of repeats. So while this seems relatively simple, you can now consider adding 2, 3, 4, 5 more of these vehicles, all with different capabilities, potentially different sensors, different battery life, different phenomenon they're trying to observe, the fact that the ocean is really hazardous, that we don't really know what's going on down there at all times. So this can kind of be a lot for scientists and engineers to manage just by hand. And because this process does take, like a few hours, and you have to wait and get the data back and redevelop a new plan, you're kind of limited in the amount of science that you can do. So our team's goal was to try to design an autonomous system capable of taking over a lot of these operations so that the scientists and engineers could really focus on science and engineering and not kind of controlling and managing this fleet of vehicles. And we want to kind of have the vehicles have as much smarts as possible so that we can really just focus on the science. So what does that sort of architecture look like? So one thing we can ask to kind of guide our design, which is what we've done, is kind of what makes a human a good explorer? How can we design an autonomous system to be a good explorer using these kind of principles? So the first thing is we are adaptive and predictive. We can take in information about our environment and change our behavior accordingly. We can also kind of predict what's going to happen next. Another thing, we're goal-directed. You don't have to be told exactly what to do at what time. You can just say, I want to make breakfast. And then that there's a number of different activities that you have to do to make breakfast, but no one has to spell it out for you that you have to open the fridge and take out the milk. So we want a system to be able to do that. Another thing, we make schedules, we make plans. We're able to kind of think ahead about what our final goal is and plan intermediate steps to get there. We're self-preserving. We are going to try to keep ourselves safe in this process, whatever we're doing when we're trying to explore a new environment. And we can coordinate with others. So if we are exploring a new environment or doing a task with others, we can make sure that we are utilizing our collective resources together. So my team kind of tries to take these principles and design an autonomous system that kind of encapsulates these ideas. So what does that look like? I present the Enterprise Autonomous Crew. So yes, in an abundance of nerdiness, we have named our architecture after the Starship Enterprise, which I'm sure many of you have seen the Star Trek movies. And I kid you not, this is what the names of our algorithms are called. So starting from inputs from the scientists here, we have, goes through this whole architecture of decision-making components to control a fleet of autonomous vehicles to do some sort of exploration task. So Enterprise is a huge architecture. There's a lot of work done by myself and by a lot of my lab mates and lab mates before me. And there's actually a lot more involved than what you see here, but I did want to kind of give you a flavor of what each of these algorithms can kind of do. So first we have Ahura, the communications officer. Ahura is responsible for coordinating with the humans, specifically the scientists, the engineers, and the crew on board to kind of make a high-level schedule of the day or of the whole kind of underwater campaign, taking into account all the resources. You have personnel, you have boats, you have cranes, you have, people have to sleep, people have to eat, and so all of this kinds of thing have to be put together into a schedule. And the humans can negotiate with this autonomous system, Ahura, to say, my preference is that we get, 3 vehicles in the water, but if we can get 4, that's great, but I'm okay if there's only 3. So we can kind of talk to the scientists in that way to make the best schedule possible. Next, we have Spock, the scientist. Spock is responsible for, Spock uses a mathematical model to reason over a set of science variables, like maybe we're interested in coral reef density or water temperature. And based on real scientists' understanding of this environment prior to exploring the area, Spock can kind of use its mathematical model to pick some locations that we think might be good to visit that will give us a lot of information autonomously. So that's what Spock is doing. Next, we have Kirk, the captain. Kirk takes in information about the schedule from Ahura and information about the science locations from Spock and kind of creates a step-by-step activity plan for how to achieve those goals within the schedule. So if we had something like, we want to take pictures of these 3 locations and we need it to be done in 2 hours, Kirk will kind of divide this high-level goal and generate a activity plan that will kind of step-by-step guide the system to achieving those goals. So now this is the activities, but another really important aspect is the motions. Next down in the line, we have Scotty, the engineer. Scotty is responsible for coordinating the motions of multiple vehicles that might be coupled together. For example, on this little GIF that you see on the side, we have a ship in blue that has to drop off an autonomous vehicle in red to visit locations A and B while maintaining a communication distance so that the 2 vehicles can stay in communication a lot. And we have interconnectivity like this a lot on these missions between different vehicles that maybe 2 vehicles can't collide with each other, or 2 vehicles have to stay within a certain distance of each other, or we know that the ship has to pick up 1 vehicle before its battery runs out. So Scotty kind of coordinates that motion plan when we're thinking about all the vehicles together. And then finally, down here at the bottom, we have Sulu. Sulu, the pilot, is responsible for lower level single agent motion planning. So this is just the path of a single agent traveling through the water. And Sulu is special because it takes into account the uncertainty in the environment. So we have currents. We're not actually sure explicitly how the agent might behave underwater, but we have a model for that. And so we want to generate a plan that takes into account all of this uncertainty and all of this risk, and generates a plan that has a very low probability of colliding with any obstacles. And what this might look like is you might have a path that kind of takes a wider berth around obstacles, because we're not actually sure where we're going to be along this path at any given time. So that's kind of the components on their own, but really the enterprise system is a continuous system. All of these components are constantly talking to each other, and giving feedback so that these vehicles can operate unattended for long periods of time. For example, we have the vehicles themselves, when they collect data, send it back to Spock to generate new science sites for us to visit based on the data that we just collected. Scotty and Sulu gives information about the paths that the vehicles are going to be traveling in, so Kirk knows, make sure that all the vehicles are actually staying within the allotted schedule that they were given. Additionally, Kirk can report back to Uhura when maybe some of the goals aren't going to be met in time, and Uhura can negotiate with the scientists and the users to say, hey, this goal is not going to be satisfied, we're going to miss this deadline, or one of the vehicles, has broken and it's now out of commission, how are we going to modify the plan? And so all of these things are working together, continuously planning and executing a mission in the world. And you can see how this particular set of crew members, autonomous crew members, takes a lot of the burden off the scientists, where they can focus on, here are the high level goals, and then here's the data afterwards. So how do we actually use this system in the real world? So just this past November, this is one of our missions. We explored with the Woods Hole Oceanographic Institute and the University of Michigan. We explored the Colombo volcano, which is an active underwater volcano off the coast of Santorini, Greece. The volcanologists we were working with are really interested in this area because there is hydrothermal vents that we think they think have extreme forms of life that can survive in these really extreme environments, which also gives us clues to where life might be able to survive outside of Earth, elsewhere in our solar system. We were also really excited about this place because this is a relatively unexplored volcano. There's not a lot of people, divers, teams that have gone down in this volcano, so we really got a chance to test out our system and how it explores an unknown environment. We were working with two different types of vehicles. This guy up here is called the Nereid Under Ice, which has a manipulator arm, and it can kind of grab things and take samples down in the environment. And then we were also working with these gliders, which are kind of more like reconnaissance vehicles that are doing scouting, kind of doing long range paths to kind of explore the area. All of these were being deployed from this very, very cool looking cable-laying ship. And up here in the corner, this is our little tiny office on board this ship that we had in November. So that's what it's like to work on a ship. One thing I did learn, and I want to emphasize, is that a lot can go wrong when you're working in the field. We had so many things go wrong on this mission. First, our Nereid, this underwater manipulator, was almost lost under the ice in a previous mission. So our entire mission was almost canceled because of that, but we found the vehicle. That was exciting. We got to Greece. Many of our operations were delayed because our glider's batteries took a detour in Germany, little side vacation to Germany. So we had to wait for those to get to us. And even during our operations, when we were actually finally on the ship, finally deploying our vehicles, one of our gliders got kidnapped and was held for ransom by a local fisherman, and we had to rescue it. So there's a lot of things that can go wrong, but we were able to do some pretty cool science. This is an example of one of the paths that our system planned autonomously from science information sites chosen by Spock. This arrow here is a hydrothermal vent that was previously undiscovered, that we discovered during this expedition, and it's now coined Spock's candle. And so that's really cool. We discovered some new science autonomously, and the scientists and volcanologists that we were working with were really excited about that. So that's kind of the work that I've done in the past. What kind of is the work that I'm interested in to do in the future? So one of the things I'm really interested in next is this area topic of active sensing. So I've been focused on execution, which is basically like how can we reason while an agent is performing actions in the real world, take in information and improve their behavior over time in response to the environment. Looking forward, I'm interested in active sensing, which is basically planning motions to improve your sensing capabilities. A really great simple example of this is imagine you're in a car on a very narrow road and you are stuck behind a truck. And you would like to go around this truck, except for that you can't actually see if there's an oncoming car in the opposite lane. So you need to kind of do some maneuver that might not get you around the truck, but will maybe give you a little bit more information about the environment. You know, how we kind of nudge around just to see if there's any oncoming cars before committing to making that whole maneuver and going around the truck. And so these kinds of information gathering maneuvers as it relates to sensing is kind of what I'm really interested in. And it applies in a lot of other contexts, like in the underwater context. If we kind of are aware of what our sensing capabilities are, we can kind of plan motions that will improve our ability to not only sense science, but to sense obstacles and hazards in the world. Yeah, so that is a summary of my research. Thanks for listening to this fire hose of information that I just gave you. And now I definitely want to open it up to questions from you guys. Thanks.
Thanks so much, Marlyse. Do you want to stop sharing your screen? I'm going to share mine and just remind folks about how they can ask questions. So we'll be using the Q&A pod or hand raising to ask questions. And we can do that now. So, and while folks are beginning to enter their questions, so for those of you that are on Zoom, you can use the Q&A pod to submit your questions. And then if you don't have a question of your own, but maybe someone else has asked a question that you're interested in knowing the answer to, you can pose that question there too. So while we're doing that, one of the things I wanted to kind of talk with you about, Marlyse, is I know that in your work with women in STEM and the various outreach work that you do, you talk a lot about role models. So I've shared some fictional role models here. I'm kind of curious if you have had a leaning towards any of these various fictional professions or role models in real life that have really guided you towards this work.
Yes, well, just looking at the set you have here, Indiana Jones hits very close to home. I love Indiana Jones movies, very much the explorer. But in real life, yeah, I definitely was really motivated by my parents. My mom is a super awesome, powerful woman who kind of translated a lot of those lessons down to me. And then in my professional life, I definitely have had a lot of female professors at MIT, which unfortunately there's not as many as I would like there to be, but a lot of female professors at MIT who not only have led me by their example, but have been a super awesome people to bounce research ideas off of and kind of talk to about kind of more real life things. I think having role models is really important. And it's also really important to be a good role model yourself.
Great. So, we do have, so many of our students that are joining us here today are part of the North Anglia family of schools, and they have an area on their Moodle, I guess, called Global Campus, and they've already done some background investigation about your work, and so they had some questions in advance. So I'm wondering if there's one here specifically about robots programming and which language you use to create software.
Sure, so I can answer that question. So we use a lot of programming language, probably some that you've heard before. We use Python and C++, and maybe one that you haven't heard of is Lisp. Those are kind of our main languages that we use. And then we also have a lot of other kind of development tools that are really important, like GitHub to manage our code. We use Docker kind of to set up our whole architecture. We use something called ROS, which is the robot operating system, which is basically an interface between an actual robot and higher level code. And so that's really great that we use. Those are kind of like the main things that we use. And we're always adding things to our repertoire of not only programming language, but tools, and trying to develop our own tools and own languages. We actually have developed our own language for high level modeling of these autonomous missions.
And the same student from our Oak Ridge International School is also asking what kinds of precautions you consider while launching robots under the sea.
That's a great question. I think the biggest one, I'll say the biggest two. The biggest two are communication. We often aren't able to communicate with vehicles underwater. So this means that we have to schedule and plan times that we're going to communicate with these vehicles, not only to receive data from them, but also to make sure that they're okay, that they're safe. And that's the other big precaution, is making sure they're safe, designing trajectories and paths for the vehicles to take that are going to be avoiding obstacles, avoiding areas with really high current, avoiding areas where there might be other ships passing by. And that's also often kind of hard to do because we don't know a lot of those things in advance. And so we're kind of planning on the fly in a lot of cases to do that. Yeah, I would say those are the two biggest things.
All right, we have a question from a couple of students that want to ask them verbally. So I'm going to take a question over the phone. Hold on one second. So Hirikesh, I think you should be able to ask your question.
Yeah. Hi, ma'am. So I would like to just ask, how big the robot might be.
Great question. Can I share my screen again?
Sure.
Okay. I just want to show some context. Okay. So you can see my screen. These are a ton of different robots that we might that we have deployed in the past. If you see this guy over here with the flag, this is about half the height of an adult person. So they're pretty big. This guy over here, this is called Sirius, this double layered yellow tube one. This is probably taller than myself, definitely probably taller than a 6 foot person, like a grown adult male. And then these ones are about kind of in length. The gliders are maybe a little bit longer than an adult arm span. So that's kind of the size of some of these vehicles. And I think if I go back, let's see, a couple pictures. Let's go way back. Here, you can kind of see scale when comparing to humans. So these guys are sitting down here, and you can see Sirius in the background. It's pretty big. So these are pretty big vehicles, which adds to the challenge because you have to deploy them using kind of cranes and interesting mechanisms like the one you see in this picture. And you also have to be super careful when they're operating underwater, avoiding narrow canyons and things like that to make sure that they're not colliding with underwater hazards.
So we have another question from the Q&A that's kind of related to, or talking about your autonomous vessels, and wondering about, are they getting kidnapped by fishermen? Are they able to sense live threats? What kinds of sensing of danger do they have?
Yeah, so I will talk about the gliders. These are the ones that kind of look like big torpedoes. They have a lot of different sensing capabilities. They have sonar. So basically there's a sonar that's kind of radially going around and sending out sound waves and then receiving them back, kind of like how dolphins and other things kind of echolocate underwater. So that's data we use to sense obstacles, but there's also other things that we combine. There's an altimeter, which uses pressure to say how deep we are in the water. We also have a mass spectrometer. This is something that actually can analyze water samples to say what chemicals are in the water around us. We also have just simpler things like temperature sensors, like regular cameras on board. And so kind of trying to fuse all of these sensors together to understand a picture of what's actually happening is pretty challenging. Especially because oftentimes the computing power on board one of these vehicles isn't super large. So we can't just, take in all this data and run some machine learning algorithm on board and spit out the answer, because we don't have that much computational power on board. And so we have to find other ways to kind of use the sensor information. In terms of sensing danger, the sonar is able to sense kind of the topology, the landscape of the sea floor around the vehicle. People have often asked us, do we see fish? Can we avoid that fish and things while we're underwater? Certainly we can, definitely harder, because fish are so unpredictable and often are only there for a fleeting moment. And in terms of getting kidnapped, that often happens when the vehicle surfaces and is sitting on the surface. When the vehicle is sitting on the surface, it doesn't actually have a lot of control over its own mobility because these are gliders. They're designed to operate in the water underwater. And so they kind of just float there for a while and wait for us to come pick them up. And these are the times when a lot of times other people who are, fishing or doing other things in the waterway will come and grab our vehicles. Mostly out of curiosity, not out of anything bad. And we have to then go rescue them from these other unsuspecting fishermen.
Fishers of curiosity. So we have some questions about whether or not you feel like robots could help. Right now humans are dealing with the COVID situation, and that's a dangerous situation for humans. Do you see the opportunity to use robots to intervene and maybe have medical applications?
Yeah, that's a great question. I don't have a super yes or no answer. I think robotics and AI are super powerful. I know a lot of my peers are working on more on the computer science side, modeling how the disease is progressing, how different safety measures predicting how different safety measures will be impactful, if they'll be impactful at all. And then there's also on a lower level, just people doing, manufacturing, on the manufacturing side for PPE, protection equipment, for masks and goggles. That could be a great way to do it. But I think this does bring a huge light to kind of other things that we've been talking about in the world that haven't happened yet, but that could really help with COVID. A great one is Amazon Prime Air, autonomous drone delivery. Deliveries are a huge deal right now. It's really hard to order from Amazon, and that's a place where people come into contact with each other. And so imagine if we had autonomous delivery systems that would take humans out of that equation. So there are things like that. I think autonomous delivery is probably the one that jumps out at me as being the most impactful.
Mm-hmm. And another attendee asks, how do you connect the hardware of the robot with the software or programming commands?
Great question. So the vehicles have computers on board. The computers have a small amount of power. They're able to do some reasoning on their own. And we kind of just very simply use, a USB cable to upload code to those to those vehicles most of the time. And then a lot of times for data transfer, or if we are extending, a larger plan to the vehicle, sometimes we do computation off board on a computer that we have, sitting on the ship. And then we send it over, acoustics, we send it over satellite communications, we send it via Wi-Fi if the vehicle is on the ship with us. to get data to the ship. Yeah, to get data to the autonomous vehicle.
So let's see. How many people are in the group that are working on this project, and how do you differentiate roles? How do you interact with your colleagues? How do you know how your particular work fits into this overall project, which is so much larger?
Great question. So within my lab, there are about 8 of us who are working on the enterprise architecture that I talked about. And roughly there's about a person for each of those components that I talked about. There's someone responsible for Spock, there's someone responsible for Kirk, Uhura. I'm personally responsible for Scotty. And so that's kind of like how our responsibilities lay out. However, there's a lot more that goes into that. First of all, we have to work together a lot to figure out how are our components going to interact, how are they going to talk to each other, what information does my algorithm need from your algorithm, and that's a lot of work, and that's a lot of collaboration. And then beyond that, we work with roboticists. So we don't actually own, my lab doesn't actually own any of the vehicles that I showed you. Those are all owned by marine roboticists that work at the Woods Hole Oceanographic Institute or the Australian Center for Field Robotics. And so we have to work with those people to say, how is our code going to work with your robot? So that's another really close relationship. And then on the other side, we have to work with the scientists, so the volcanologists, the marine biologists who are actually interested in the data that we're going to be collecting to say, what are your goals for the mission? We have to understand what their priorities are, what their timeline looks like. And then from a very low level perspective, we have to work with the crew on the ship. So there are a set of crew that is operating the ship for us. And they, do all the things like deploying the vehicles, driving the boats out to get the vehicles, setting up this whole environment, driving the actual ship, all of that good stuff. And so we have to work with them to make sure we're respecting their work and respecting their time. They have to sleep. We all have to sleep. And so there's a lot of collaboration and interconnectivity that goes on, both within our team and also with all the people that we have to collaborate with to make, something like these underwater deployments happen.
That's really interesting. So I'm curious about your partners. Do they have all kinds of other groups that they're also working with, and who, how do all those moving parts get managed?
That's a good question. So typically what happens is a number of institutions will collaborate on some sort of project or proposal. And you can imagine there's probably at least 20, if not more, different expeditions going on at any given time, throughout the year. So with different vehicles, with different organizations. So yeah, for example, we're doing 2 this year, I think, one in the Arctic and one in Australia. And so we kind of just, we talk to the people who have the robots and are interested in doing science, and we say, hey, are you interested in having some autonomy on board your robot? And then we can kind of collaborate with them. And yeah, so it's really just kind of trying to find a synergy between the science they're interested in collecting, the engineering technology hardware that they're interested in testing out on the vehicles, and then our autonomy and computer science that we're interested in testing. And there's usually a lot of opportunities to do that. As I mentioned, the ocean is a huge place. There's a lot of things to do there.
Yeah, so we have another question about whether or not there are limits to the autonomy of the machine. And also, in many of these areas of growing technology, we see accompanying ethical questions that come into play as you are a designer or a developer working on solutions to these challenges. Are you facing any of those questions as part of your work?
Yeah, so particularly in the underwater case, there are definitely limits to the autonomy. The system that I showed is a very bare bones of what actually is involved, and it's actually really hard to get that to work. And we have to be respectful of the environment. First of all, we are entering into new places where there hasn't been technology before. Like in this underwater volcano, there hasn't been any sort of underwater autonomous systems down in there. We have to respect the environment. And a lot of other things we do, like exploring coral reefs, we have to be really careful and above all else prioritize the safety of not only the environment, but also of the people who are working with us and with the vehicles. And so that's kind of like where we see the ethical questions in the underwater case. My lab does a lot of other things as well. Outside of the underwater robotics case, we have involvement in self-driving cars, which, as you can imagine, there's a lot of ethical issues that come up there, as well as kind of in manipulation and household robotics. So robots that have to operate around people very closely. And so there are also issues about, human safety when it comes with working very closely in close proximity to another autonomous system that we have to think about. I think that these ethical questions are super important, and I often feel that people in academia don't consider them as much as they should, but we definitely try to keep that in mind when we're designing our algorithms.
Great. I'm going to take another audio question. So Vivek, you should be able to answer your question now.
I was just wondering, so you know how you send satellites out? Do you think you could be able to replace that every satellite with a smaller, more modular satellite so that it can become easier for space exploration and future satellites?
That's a great question. I think that exactly what you're describing is where the industry is headed. People are seeing that sending out those big, huge satellites that we've done many times is really expensive, takes a really long time, and limits the amount of science that we can actually do because it takes so long for any one thing to get on board. So as you're seeing, as we speak, kind of the rise of CubeSats are kind of are coming about. And if you look at a lot of the missions that are happening or upcoming, almost all of them have some sort of CubeSat opportunity. That is to say that the main spacecraft that's carrying whatever, for example, the next time we send something to Mars, there is very likely to be CubeSats also on that spacecraft that will be jettisoned at various points in the trajectory to do intermediate science along the way. And those CubeSats are being developed by university students, high school students, like people all over the world who are trying to do really cool science. So yes, the modular design is really important. I think as we push further out into the solar system, we're going to see more systems that have multiple agents all cooperating on the same task. For example, there's a lot of ideation around the Europa mission, and the Europa mission is likely, when it eventually happens, going to involve not only a satellite but also a lander and also an under ice vehicle and maybe some CubeSats and a lot of things kind of all interconnected, which isn't something that we've done a lot before in the space side, except for around Earth, maybe. So that's going to be really exciting. And I think, modularity is definitely the way of the future.
Okay, it looks like Hassini has a question for you too, Marlyse.
How many people work together in this whole process of making a robot?
How many people? Lots of people involved. So there are, as I mentioned, 8 people on my team, but there's 20 people in my lab as a whole, and everyone in my lab helps out. And then I would say on a given, if we're talking about a given operation, like a given underwater operation, like our Santorini mission, for example, there was, I think, 5 of us from our lab. Then there was probably 4 to 5 people from the 2 other labs that we were working with. Then we had probably about 10 people who were just crew for the ship. who were there. So add that up in total, it's about 25 people. That's just in one mission, not including all of the other people that didn't get to actually be on the ship. So I would say for any one of these, ocean operations, there's probably about 50 people involved. In terms of actually building the robots, that's also a whole other process where you have a manufacturer that's probably hundreds of people involved in building one of these big robots, and then you have the engineers who modify it with the sensors and everything. So it's a big process.
So we have a couple of questions about sort of the materials and limitations of the physical limitations of the robots for underwater manipulation, including temperature limitations.
Cool. I actually don't know the actual material that I know the most about the gliders, but I actually don't know the material that the gliders are made out of. I do know that the gliders are rated to about 5 kilometers, I think it is, under the water, is their like limit in terms of the depth. In terms of temperature, I also don't have a hard number there, but I would say like definitely not hotter than like 90-ish degrees Fahrenheit. So we have to be careful, especially when we were operating in those underwater volcanoes where there are hydrothermal vents with like really hot material coming up out of the earth. We had to be careful in those areas because if the vehicle passed over one of those areas, a lot of the sensing capabilities would be limited or sensors would be skewed. The sonar kind of bounces off of particles of warmer liquid, and so like it definitely messes with our sensors. I think the vehicle is able to survive in that, and then they're able to survive in a lot of really extreme environments. For example, we're going to the Arctic in a couple months to do an Arctic under ice mission. We're sending one of these gliders like to track the movement of an ice shelf. So like those are super freezing waters, and the vehicle is going to be totally fine, which is kind of a really cool thing about these underwater vehicles is that they can go so many places that humans can't, and be underwater for such a long time, and it's really allowing us to do so much more exploration of our oceans.
That sounds like a very exciting mission. Do you have a favorite mission that you either have done already or that you're looking forward to?
So we did one in 2018 January in Hawaii. That was the first one I got to be a part of, and I think that has been my favorite so far. We weren't really doing that much specifics. There wasn't a specific science goal. The kind of goal of the whole mission was how many of these vehicles can we control at once? And we had a bunch of different, that's the picture that I showed at the very end of my presentation, was controlling all of those vehicles. Mm-hmm. And all those vehicles, they had so many different capabilities. There was one that stayed on the surface. The vehicles could move differently throughout the water. There was one with a manipulator, one that kind of just floats around and bobs around in the water. And so it was really cool, one, to work with all these different scientists and people who came along with these vehicles, and also just to see our algorithms, see my algorithms for the first time working in coordination with the rest of my lab and in coordination with these vehicles was really, really cool.
Great. So I want to end with a question. Most of the folks who are participating today are students. And so I'm curious if you have any suggestions for the students that are joining us here today, if they want to pursue work in the STEM field or robotics or underwater robotics. What suggestions do you have for them? If you could speak to your 13 to 17-year-old self, what advice would you give?
I guess a biggest advice is coding is the way of the future, in my opinion. Regardless of what STEM field you're going to be in, you're likely going to be doing some coding. I have friends who are nuclear engineers, who are environmental engineers, and they're doing some coding. So I would start with that. And there's so many resources online to walk you through. You can teach yourself. I mostly taught myself. When I was in high school, my high school didn't have like a computer science class that I could take. And so I kind of taught myself through the robotics team that I was a part of, how to code. And even if it's just a little bit, I think that's definitely a great way to get started with coding and AI and algorithms. Other than that, I think it's just like staying curious, you know, reading articles that are interesting to you. I think if you have the opportunity to join something like a first robotics team, or robotics team, or it could be any sort of like team, engineering team, even if it's one that you start yourself, or even if it's just you and your friend in your house building, I don't know, a skyscraper out of blocks, I don't know, whatever it is. I think just getting your hands dirty and making something work, which is what robotics did for me, was super rewarding and taught me kind of like a lot of problem solving, a lot of collaboration skills, and kind of like quick thinking that was helpful going forward.
Great. It sounds like building a community of people with similar interests is also a powerful element of that.
Very true. Yes.
So find your people. Yeah. Okay. Great. Thank you so much for joining us today. It's been great to hear about the work of your team. For those of you that are interested in hearing some more of our episodes of the Firehose Chat series, our next one coming up is featuring Amos Winters, who is in the Gear Lab here at MIT. And they work on developing resources and solutions for developing nations and emerging markets. So for those of you that are connected to some of the UNICEF sustainability goals and work on those and think about those each year, you might be especially interested to hear about Amos Winters' work. We also have Aran Agozi on May 27th. He is the founder of Harmonics. He's also a professor here at MIT in the music technology program. And some of you may recognize his work as part of Guitar Hero. So he's been able to mesh his passion for music and technology and entrepreneurship into a very interesting career path for himself. And then on June 10th, we'll be hosting Georgia Van de Zan, who's a graduate student here at MIT, and talking about introducing key concepts of engineering and mechanical engineering through toy design, and how we can kind of introduce those concepts to ourselves and our students through playful mechanisms. So we hope that you'll be able to join us for those upcoming sessions. And would like to thank you to our sponsors, North Anglia Education and Cambridge Science Festival. Without your support, we really wouldn't be able to do this work. So we really appreciate being part of your community. So thanks again for joining us, everyone. And for those of you from the North Anglia family, we will be posting the recordings of these sessions to the Global Campus, and that should be up in the next couple of weeks. So, and then for those of you joining outside of the North Anglia family, we will be sharing the recordings on Cambridge Science Festival and MIT Museum sites. So we hope that lots of you have an opportunity to benefit from Marlyse's journey in STEM. Thanks all so much for watching.